Uh, Hello, good morning. Our presentation topic is Sg-Admm, that is Semantic Graph-Regularized ADMM for collaborative filtering. So the main objective of our project is overcoming cold start and topological sparsity via entanglement, right? So you imagine launching a massive streaming platform today. Most algorithms depend on vast user interaction history to make product recommendations. But what happens when you introduce a completely new movie today with zero user clicks? Most classical recommender systems instantly fail. Today we present Sg-Admm, right? Our novel mathematical architecture that inherently solves this problem by using language models while breaking the severe computational gridlock that normally plagues geometrical graph topologies. So my project members are Vinayak Agarwal and Arjun Kumar. So the core problem, right? To understand the core problem, consider how algorithm works, right? Models like matrix factorization break down a massive grid of user clicks to discover hidden preference patterns. However, in the real world, this matrix is over 99% void because users don't give feedback to each and every item majorly, right? And also if you introduce likewise I give the previous example. If you introduce a new movie, there will be very few clicks available, right? And you need to recommend that item. When a completely new item is cataloged, right, it has no interaction history. The algorithms are structurally blind to it. It remains entirely disconnected from the ecosystem, resulting in dreaded cold start crisis. To rescue these undiscovered items, previous research leans on semantic homophily. The intuition is simple: if two products are linguistically similar, right, they belong together algorithmically. Take a Amazon Music dataset, a Fender Capo that you see on your left side of the screen, and a Kaiser Capo may have strictly zero overlapping buyers, but by pushing their product description through a large language model, we realize they describe the exact pushing the same concept, right? So they are these two products are pushing the same concept. We can artificially graph a connection between them, effectively allowing the new cold product to borrow the heavy recommendation momentum of its older popular neighbor. While linking item works conceptually, injecting this directly into traditional math creates catastrophic processing bottlenecks. Notice the standard loss equation here, right? Um, the graph Laplacian L directly forces product Vi to update simultaneously alongside its sprawling neighbors Vj, right? This mathematically locks the systems. Deep graph neural networks forcefully drag all the connected neighbors closer together repeatedly. In highly sparse environments, recursively blending these nodes causes them to lose their unique individual characteristics entirely. A fatal flaw we call over smoothing or catastrophic over smoothing. So coming to our methodology, let's trace the data natively through our architecture pipeline. We begin on the left with inputs and pre-computation. We take the traditional sparse interaction matrix where Alice, the guy, uh, clicks movie A while simultaneously computing the semantic Laplacian independently from textual metadata via transformer encoder, which is like a part of the language models. The magic happens centrally in our ADMM optimization loop, which is at the center. The semantic graph exclusively constrains the auxiliary z step, entirely isolating the network math from the classical U and V matrix updates. Because of this decoupled topological safety net, as you see on the right in the final latent embeddings output, the system gracefully pulls LS and movie directly towards matching sci-fi items purely through a semantic momentum, perfectly executing cold item prediction. This is precisely where our architecture contribution intervenes. Uh, Sg-Admm breaks the mathematical tension entirely. We explicitly separate the core recommendation engine from the rigid language network structure. By utilizing the alternative direction method of multipliers, we introduce specialized auxiliary variable z. Uh, this allows the matrix solver and the semantic graph limits to operate completely independent in memory, syncing up cleanly without ever mathematically entangling their gradients. Then this is like algorithm step by step overview. Let's walk through our internal algorithm operation step by step. Since we cleanly decouple the environment, we can process highly isolated optimization blocks. First, we independently update user preferences. Second, we update item factors independently. Then comes our major innovation, step 3. Rather than deploying exhausting multi GPU graph message passing routines, we resolve our textual matrix constraints physically using a static sparse uh, Kolsky pre-solve. Because the text graph never changes during execution, we cache the matrix structure once, meaning solving it takes absolutely invariant constant time. Datasets and evaluations metric. To rigorously benchmark our framework, we deliberately tested out two extreme configurations. We used movie lens 1 million to track a dense, highly stable environment. More critically, we utilized Amazon Musical Instruments, a chaotic, deeply sparse dataset where the cold start problem is massively prevalent. We measured empirical success using hit ratio to verify if accurate products appeared in the top slots, and NDCG metric if the highest probability products were actively sorted first. So these are the baselines which we compared to. We pitched our formulation directly against the past decades premier models. For linear stability, we verified against traditional matrix factorization (WMF), and current Reening baseline is by stack. To strictly test against modern geometric assumptions, we heavily benchmarked against complex deep neural graph architecture like light GCN and NGCF, explicitly comparing our non-coupled network approach to their highly coupled multi-layer message passing. Then coming to the main results, uh, basically the results structurally validate our decoupling hypothesis, right? Thesis on the punishing Amazon dataset, the deep geometry multipass networks utterly collapse. You can see NGCF and light GCN fall profoundly low as their deep convolution trigger over smoothing. Sg-Admm conversely entirely avoids this. Our algorithm produces a striking 3.2% relative lift in hit ratios against traditional matrix factorization limits and other baselines, right? So 2.2% with respect to NGCF baseline, and it basically consistently beat out the highly competitive ease baseline across both the metrics. Now coming to our ablation studies, right? So we formulate our ablation studies through our six research questions, right? So this is research question first. In research question first, we questioned if our semantic graph structure was truly required. We tested variants where we deleted the graph entirely, or worse, injected fully random edges. The data proved unequivocally that basically it proved that utilizing language embeddings creates a distinct homophily spike, like random edges actively poison that gradient bounds entirely. Then this is research question 2. Research question 2 questions computational load constraints. With LLMs, the assumption is usually bigger is better. However, when we swapped lightweight 22 million parameter mini LM extractor with a gigantic 109 million parameter network, the recommendation performance barely shifted because Sg-Admm explicitly filter graph geometries independently. It forces highly intelligent routing without requiring massive GPU language generation overheads. Then research question 3 tackles a traditional critique of separated ADMM equations. Are they too fragile? The turning parameter row dictates the penalty strictness, enforcing similarity between our matrix solver and a graph topology solver. By exponentiating this hyperparameter over limits traversing 100 times variance, the accuracy curves remains virtually dead flat. Unlike brittle graph neural networks, SG-ADMM intrinsically guarantees industrial deployment for formulation stability as well. In research question 4, we basically analyze exactly how many semantic friends a product should connect with. We If we allow k equals to 30 neighbors, the graph dilutes feature representation, causing mild accuracy smearing. If we forcibly restrict edges, the item starves for contextual interaction history mapped across testing grids. Isolating the algorithm explicitly at k equals to 15 neighbors structurally extracts ideal similarity boundings. Research question 5 ensures that deep graph enhancements don't break proven classical collaborative matrix theorems. Alpha controls how loud we treat a user's single click mathematically across empty voids. Scaling this parameter reveals that our architecture structurally tracks identical legacy alternating least squares theory, dynamically speaking precisely at historical 40 times multiplier states natively. Finally, inside research question 6, we examined the physical capacity of the latent factor embedding matrices themselves. When we constrained spaces to 16 features, structural bounds collapsed. However, forcing highlights that data gap inherent sparsity limits naturally bounded operations long before processing dimensions becomes an explicit barrier. In conclusion, SG-ADMM functionally solves one of the most stubborn structural network intersection recommender systems and geometrical machine learning in a way. By tearing apart the structural network mapping from empirical matrix gradient algorithms, we mathematically halt node over smoothing and fundamentally rescue sparse cooled items with staggering greater than 29% bounds with some baselines and 3.2% lifts on the classical graph frameworks like NGCF. We have published our full Python architecture natively inside the paper repository for reproducibility text testing. And thank you.